Shall I start the class? Why the strength is very less today? Am I audible? Okay, okay. Okay, let us start today's class, ma. What we have discussed yesterday, in the yesterday's class, we have discussed how to perform multiplication operation on a signed data. Multiplication on signed data. As well as we have seen how to perform addition and subtraction too. Now, every integer can be represented in three ways. You can represent an unsigned integer in three ways, right? Signed magnitude representation, signed ones complement representation, and signed twos complement representation. So in the last class, we have seen how to perform the multiplication on signed magnitude data. And we'll see multiplication on signed twos complemented data using Booth's algorithm. Using Booth's algorithm. What is signed twos complemented data? In this, the negative numbers, there is no specific sign. The sign of the number is not specified in the number itself. In case of signed twos complemented data, the negative number, let me record the video. Sorry, I forgot to record. Okay. So in case of signed magnitude data, the sign of the number is specified explicitly. Further, the MSB bit is used. But in signed twos complement data, sign of the number is not included. No MSB bit or LS. No bit is specified or allocated for sign of the data. The sign is included in the number. That means you will represent the negative number in a 2's complemented data. If it is signed 1's complement data, the negative number is represented using 1's complement. Now we'll see the multiplication using Booth's algorithm. This is the algorithm. This is the flowchart of Booth's algorithm. So what is for multiplication? You require a multiplier and a multiplicand. I am going to store the multiplier and multiplicand in two registers. Multiplicand I am storing in BR. Multiplier I am storing in a register Q. Right? And I am going to store my result in an accumulator. So before you start, there is nothing in the accumulator. So initially the accumulator is equal to 0. The accumulator is equal to 0. And we are taking one more bit, Qn plus 1. A new bit we are considering and we are initializing it to 0. Qn is the last bit of the multiplier. And one more bit I am considering as Qn plus 1. It is equal to 0. And you know what is the sequence counter? Sequence counter is equal to the number of bits in the multiplier, which is n. Right? Now, first condition to be checked. What is the first condition to be verified is check the value of Qn and Qn plus 1. Two values, Qn and Qn plus. The combination of Qn and Qn plus 1 is to be verified. So, how many different possible combinations you can have for two numbers? Obviously, for 0, 0, 0, 1, 1, 0, and 1. If this combination is 0, 1, then perform the addition operation to the accumulator, add the content of BR, that is add the multiplicand and store the result back into your accumulator, that is into your AC. If it is 0, 1. If it is 1, 0, perform the subtraction operation. Subtract BR. In other two, 0 or 1, 1, 0, 0 or 1, 1, then perform arithmetic right shift on AC and QR. After performing arithmetic right shift, decrease the sequence counter. And this is the common step for all the possibilities. If it is 0, 1 or 1, 0 or 0, 0 or 1, 1, this is the common step to be performed. But if it is 1, 0 or 0, 1, before performing this arithmetic right shift, you need to perform either subtraction or addition based on this value. If it is 0, 0 or 1, 1, you will not perform any addition or subtraction. Directly arithmetic shift right is performed. As you are decrementing the sequence counter, at one point of time it will become 0. Whenever it becomes 0, you can stop the multiplication process. If it is not equal to 0, then continue or repeat the process. Clear? Let us see one example. Let us assume that the value of the multiplier is 10011. I am storing it in QR. Multiplicand value is 10311 and we are storing it in BN. When you see this algorithm here, we are using the 2's complement of BN to perform the subtraction operation. So I am considering the 2's complement. I am calculating the 2's complement of BR here. That is, to this 1's complement, you need to add 1, then I will get 0, 1, 1, 1. Sorry, 0, 1, 0, 0, 1. And initially, what is your accumulator? Initially, your accumulator is equal to 0. So, accumulator is 0 initially. Let us go into the process. So, this is your AC, which is equal to 0. And this is your QR, which is equal to 1, 0, 0, 1, 1. And your Qn plus 1. Qn plus 1. Initially, it is equal to 0. So, Qn plus 1 is equal to 0 and sequence counter equal to number of bits in multiplier. As your multiplier QR contains how many bits? 10011, which is equal to 5. Right? This is the first initialization step. Next, next step is what? You have initialized. After initialization, check the value of Qn and Qn plus 1. Right? What is Qn? Qn is 1. Qn plus 1 is 0. If it is 1, 0, what you need to do? Perform the addition operation. BR. What is the value of BR? BR is 1, 0, triple 1. Then, sorry. If it is 1, 0, you need to perform the subtraction operation. So, to the content of AC, add the 2's complement of BR. What is 2's complement of BR? 0, 1, 0, 1. Then you will get 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0. Next, what you need to do after subtraction? Apply a right shift operation on AC and QR. You know what is arithmetic right shift? It is not the logical shift, right? Arithmetic right shift. What is the main difference between two? In case of logical right shift, you will simply shift the bits 1 to the right side and you will discard your LSB bit, and into the MSB position a serial input of 0 is transferred. But if it is ASHR, arithmetic right shift, then at the remaining process is same. You just shift the bits 1 bit, 1 position to the right side, LSB bit is discarded, and you just copy the MSB bit as it is. So the 0 is copied as it is and perform the right shift operation. When you perform this right shift operation, this QN will goes to position QN plus 1. Next, what is the next step? Decrement the sequence counter. Here it is 5. Decrement the sequence counter. As it is not equal to 0, repeat the same process. What is that? Check the value of Qn and Qn plus 1. What is Qn and Qn plus 1? It is 1, 1. When it is 1, 1, directly apply the arithmetic right shift. Perform arithmetic right shift operation, then decrement the sequence counter. As it is not equal to addition operation, BR is to be added. To accumulator, right? So 0 plus 1 is 1, 1 plus 1 is 0 with a carry of 1, 1 plus 1 plus 0 is 0 with a carry of 1, 0 plus 0 plus 1 is 1 with a, and 0 plus 1 is 1. 1 second. Next, what you need to do? You perform arithmetic right shift. Perform arithmetic right shift. When you perform this arithmetic right shift, this Qn plus 1 will become 0 and decrement the sequence counter. As the sequence counter is not equal to 0, again repeat the same process. Qn plus 1 is equal to 0, 0. So if it is 0, 0, what you need to do? Only perform the arithmetic right shift. So copy the same MSB bit and remaining bits will be shifted 1 bit to the right side. Then decrement the sequence counter. Now the sequence counter will become 1. What is the value of this? It is 1, 0. If it is 1, 0, what you have to do? You need to perform subtraction. That is 2's complement of BR. What is the 2's complement of BR? 0, 1, 0, 0, 1. 0, 1, 0, 0, 1 is to be added. And this process has to be repeated until the sequence counter becomes 0. Whenever the sequence counter becomes 0, you can stop this multiplication process, and where the result is stored, the result is present in AC and BR. What is there in AC and BR, that will be your multiplication. Right? This is how you will perform Booth's multiplication operation. Is it clear? Am I clear? 1 second. Am I clear, ma? Is it clear now? AC and BR. AC is the one which stores the resultant, Initially, it is equal to 0. It is initialized to 0. Next, see here, ma. When you see this algorithm, 1 second. So multiplicand you are storing in BR and in QR you are storing the multiplier. And your final result present in AC and QR. Sorry, AC and QR. So values are your, actually it was not, I'll send you another image in your notes. I'll give you another image which is clear. So AC and QR will be your final result. Is it clear? AC QR is your final result. Am I clear? And okay. Is my voice clear now? Okay. Next move on to the division algorithm. And the last one is your division algorithm. Right? So here in multiplication, you'll have multiplier and multiplicand. Here you'll have divisor and dividend. Divisor and dividend. Right? So let us consider, first we'll see how to perform a division operation with a pen and paper. With pen and paper, how you will perform binary division, we'll see. Later on, we'll see how this binary division is performed in the digital computer. Right? Assume one example, consider one example where the value of divisor is 1,001. The corresponding decimal value is equal to 17. And assume a dividend as this one where the corresponding decimal value is 449,449. Right? Now, when you perform this with a pen and paper, so as this is your divisor 1,001, this is your dividend, right? First, you will generally we will take one bit at a time. First, we'll take the first bit 0. As this 0 is less than the divisor, so you cannot perform the division operation. Take the next value, put a 0 here and go to the next value 0,1. It is less than again. So first we'll consider the first 5 bits. That is the reason I am directly considering the first 5 bits of the dividend, which is equal to 0,111,0. 0,111,0. When you calculate this 0,111,0 by decimal value, the decimal value of 0,111,0 is less than the value of 1,001. So as these 5 bits value is less than the divisor value, so I cannot perform the division operation. So consider the 6th bit of your dividend. Consider the 6th bit. Then the value becomes 0,111,0. As this value is greater than the divisor. The 6 bits value is greater than the divisor. Therefore, you can proceed with the division operation. So put a 1,000 in 1 into 1 is equal to 1,001. Right? Next, perform the subtraction operation. If it is a multiplication operation, you will write the multiplicand value. If the value of multiplier is 1, the same multiplicand is copied down and perform the subtraction. If it is a division operation, you will write the divisor value and perform the subtraction operation. So here perform subtraction. 0 minus 1 is 0. 0 minus 1 is, can anyone remember what is the value of 0 minus, what is the binary subtraction rules? Binary subtraction rules. 0 minus 1 is 1 with a borrow of 1. 0 minus 1 with a borrow of 1. Next, 0 minus 0 minus 0 minus 0 is 0. Minus 1 is 1 with a borrow of 1. With a borrow of 1. Next, 1 minus 0 minus 1 is 0. That means 1 minus 1 is 0 and 1 minus 0 is 1. Therefore, the subtraction of 0,111,000 minus 1,000,011 is 1011. 1011. As this is less than the divisor, so consider the next value. Consider the next 0. Consider the next 0. Now the value becomes 10110. As this value is greater than the divisor, so here in the, this is your quotient part. In the quotient part, you can write 1 and copy the divisor here. The divisor is again 10001. Again perform the subtraction operation. Perform the binary subtraction. Then the result will become 101. As this 101 is less than the divisor, so consider the next 0. When you consider the next value is 1010. Again it is less than the divisor. So when you are considering one more 0, you should put a 0 in the quotient. Therefore, it becomes 10100. Now this is greater than your divisor, greater than or equal to your divisor. So write a 1 in the quotient part, excuse me, and copy the divisor, that is 10001. Next, perform the subtraction operation. Then you will get 110 and copy the next value, that is 0, as there are no bits in the here. As this 110 is, excuse me, was this 110 is less than the divisor, you are trying to copy the one more value by putting a 0 in the quotient, but there are no values, there are no bits in your dividend. Therefore, you can stop the procedure here and your remainder will become 110. You please take a pen and paper and try to perform, do this division, binary division on your own, then you will understand clearly. Anyway, this is not important, just for your understanding I am explaining how to perform this binary division in the computer. That is important for you. For your exam point of view, I am telling you that is important. But if you want to know this part, you please take a pen and paper and try to do on your own, right? Next, so this is the way how you will perform binary division using a pen and paper. Now, let us see how to perform this division algorithm, how to perform this division on signed magnitude data in the computer, right? You will call this algorithm, this division algorithm, as restoring algorithm. I will tell you why we'll call this as a restoring algorithm. At the time of explaining this flowchart, I'll tell you why we are calling it as a restoring algorithm. And here, one more point to be remembered in this division algorithm is, if the size of the divisor is n bits, when the size of divisor is n, the size of the dividend will be 2n. It is double the value of divisor. The value of dividend is equal to double the value of divisor. And here again we are using two registers to store divisor and dividend. I am storing the divisor in a register B and dividend I am storing in AQ register. AQ register. Right? So first, here, before you perform the division operation, we should know whether there is any divide overflow. Whether there is any divide overflow. I'll tell you what is this divide overflow. If there is a divide overflow condition, then there is no possible. Division algorithm is not possible. Let us see what is this division overflow. So you know this Q, as you are performing this division algorithm on a signed magnitude data, so you are handling the sign of the bits, right? So here QS is the sign of the result, and what will be the sign? In case of multiplication, if the sign of magnitudes is same, it can be either plus plus or minus minus, the result is plus. In the same way, if it is one of the result is, one of the sign is negative, the result is negative. Same as here in division also, you will perform the XOR operation. Why? Because if the result, if the magnitudes, sign of the magnitudes is 0, 0 or 1, 1, the result is 0, which indicates a positive number. If it is 0, 1 or 1, 0, the result is 1, which indicates a negative number. Because positive by positive is positive, Negative by negative is positive. Positive by negative or negative divided by positive is negative. Right? So, and your sequence counter is always equal to the number of bits in the division. First step to be performed is first perform subtraction of A and B. Perform subtraction of A and B. Right? A is your dividend, B is your division. Now, whenever you perform this subtraction, after performing the subtraction, check, I will explain with this with example. Check the value of E. If E equal to 1, it indicates that A is greater than or equal to B and there is a overflow. So, to know that overflow, you are using a flip-flop called as division divide overflow flip-flop. DVF is divide overflow flip-flop. When you find out a division overflow, set the value of DVF to 1. Set the value of DVF to 1. Here SC is equal to N only, ma. But actually it was given wrong here. SC is equal to N only. It is not N minus 1. Right? Let us see one example. Let us consider this is your dividend 1,001,0,0,0,0. The divisor is 0,1,1,0. How to know whether there is a divide overflow or not? How you will check is whenever you are perform, first consider the decimal value of A and the decimal value of B. If it is greater than or equal to B, then there is a overflow. And before that, you need to subtract this divisor B from the first half bits of your dividend. This complete dividend is your AQ, right? See this dividend I am storing in AQ. If the size of B equal to N, then AQ size will be 2N. A equal to N, BQ is also equal to N. Why? Because dividend side should be double the value of divisor. Now, what is the first step? Perform this subtraction operation. When you perform this subtraction operation, if this value is greater than, here divisor is 4 bits, right? Your divisor is 4 bits. Whenever your divisor is 4 bits, you will allocate 4 bits for storing this quotient. To store this quotient also, you will allocate only 4 bits. If in a register bits, if you try to store more than 4 bits, then overflow will occur. Is it clear what exactly overflow? The size of a register is N. In that register, if you try to place N plus 1 bits, more than N bit, then overflow will occur. Right? Here also, excuse me, the size of divisor is 4. So you will get a quotient of 4 bit. So you will allocate a 4-bit register to store this quotient value. And if you get quotient value more than 4 bits, then divide overflow will occur. Let us see how it will happen. So consider the first MSB, first half MSB bits of your dividend. First half MSB bits of your dividend. So this is complete dividend. First half MSB bits are 1,001. If this value is greater than the divisor value, if this 1001 is greater than the divisor, let us see how you will perform this division. Assume that this is greater than. Anyway, the value of 1001 is greater than 0,110. When you try to perform this division operation, let us see how is the quotient you will get. 0,110. You will put a 1 in the quotient bar and you will copy the same divisor here, 0,110, and perform the subtraction operation. Right? Next, when the result is 3 zeros followed by 1. 3 zeros followed by 1. So, what you will do? You take the next one, and as this is not what we call less than this divisor value. So you will put a 0 and take the next value. As this value is again 0, take the next value, and this process will be repeated. So whenever you have a 1 at this fourth position, or you obviously know that after this fourth position you still have 4 more bits. That means you still may get 4 more quotient, 4 more bits in your quotient. So total number of quotients, total number of bits in your quotient will be 5. But you have allocated only 4-bit register to store this quotient. Am I clear? Am I clear? So one more time I am repeating, ma. This is your division, right? If this is your dividend. In this dividend, consider first half. First MSB half bits. This is also your half. This is also your half. But consider MSB half bits. So consider the first 4 bits. So whenever you consider this first bit, if this 4-bit value is more than this divisor value, then you can put a 1 at the 4th bit and you will just copy the divisor here and you will follow with the next procedure. As there exist still 4 more bits after this one, so you will get 4 more bits in your quotient after this one. So what is the total size of your quotient? How many bits were there in your quotient? There total of 5 bits were there in your quotient. But as the size of the divisor is 4, so you will allocate only 4-bit register for the quotient. That means whenever this first MSB half bits is greater than the divisor, there is a chance to get a overflow value. That means you cannot perform what we call division operation. You cannot perform the division operation, right? Now you say, ma, what is the correspond? The value for 0110 is 6. The value of this dividend is 144. When you perform this what we call, when you perform the division operation, the quotient value is 24. But to represent this 6 value, you require 4 bits are sufficient. So you will allocate 4 bits for the quotient. But if I want to represent the value of 24 in 4 bits, I am unable to represent. I cannot represent the value of 24 in 4 bits. To represent this, how many bits you require? You require 5 bits, right? So those 5 bits were not there. 5-bit register is not assigned for storing the quotient value. Therefore, there occurs a divide overflow. This is what exactly is divide overflow. Right? Now, whenever you perform this subtraction operation, if your E value, this value is 1, if your E value is 1, it indicates A is greater to B, then it means that there occurs a divide overflow. So set DVF flip-flop to A is less than B. There is no overflow. There is no divide overflow, so that you can proceed with this division operation, right? Now let us see the division operation. This is your division operation. First step is, first perform shift left. Whenever I say SHL, shift left, it means it is only a logical shift, not the arithmetic. If it is arithmetic shift right or shift left, I'll specify ASHL. As it is SHL only, so it is simple logic, simple left shift or logical left shift. Left shift is to be performed on EAQ, right? Next, what you are doing? You are checking the value of E. Here, actually, this is not required, ma. Without, for E, whatever may be the value of E, if it is 1 or 0, you are performing a subtraction operation. It can be either 0 or 1 for both the condition. Actually, you are performing this subtraction operation. That means you are subtracting your divisor from your dividend. Divisor B is subtracted from your dividend. After that, after performing the subtraction, check whether your subtraction is correct or not. Whether your subtraction is correct or not. Next, after performing the subtraction operation, check the value of E. Check the value of E. If it is equal to 1, your subtraction is correct. Then you can put a value of 1 in the quotient part. Qn is quotient bit. Dividend is AQ. That means here in Q we are storing the quotient, right? So in the quotient part, quotient bit, make it as 1 because the subtraction is correct. In other case, that is if E equal to 0, your subtraction is not possible. So you can restore the value. You are restoring the value. That is the reason this division algorithm is also known as restoring algorithm. Here you have performed subtraction. B is subtracted from A. We have identified that that subtraction is wrong. The subtraction is wrong. So you are again adding that B value, right? Next, perform, decrement the sequence counter. And you know, if it is 0, the result is stored in AQ register. That in the AQ register, the result is stored in A register, remainder will present, and in Q, quotient will present. Quotient will present in Q. If it is not equal to 0, you can repeat the process. Clear? Let us see the example. Let us see the example. Consider one example where the divisor value is equal to 1,001. Excuse me. Here again, you are performing the subtraction operation. So take the 2's complement of this divisor. So 2's complement of this B is equal to 0 followed by 4 ones. 0 followed by 4 ones. What is the first step? This is your A mark. Your A 0 111 0. This is the example I am considering. This is your dividend. Dividend will present in AQ, right? Size of AQ should be double the size of B. So what is the size of B? 1, 2, 3, 4, 5. 5 bits were there in B, but in A you have only 5 bits. So take 5 more zeros in your Q. Take 5 more zeros in Q, because if it is 5, you should have 10 bits in your dividend, and I am storing my dividend in a combined register called as AQ. In AQ, we are storing the dividend. Next, what is the first step when you see algorithm? The first step is perform left shift operation. First step. Next, perform subtraction operation and set the value of Qn to 1 and then decrement the sequence counter. Right? So left shift operation, you know how to perform the left shift operation. When you perform this left shift operation, the value of E becomes 0. This LSB bit will be placed at each position and 1 bit will be moved to the left side. 1 bit will be moved to the left side. After that, what you need to do? And a serial input of 0 will be transferred at the LSB position in case of arithmetic, logical shift left. Next step is subtract B from A. That means add B complement plus 1. 2's complement of B is to be added. So 0, 4 ones is to be added to A. Then you will get this result 0, 1, 0. Next, again perform the left. Sorry, 1 second, ma. So after performing the addition operation, what you are supposed to do? Set the value of Qn to 1 when E is equal to 1. If your E is equal to 1, set the value of Q equal to 1. Here, when you perform this addition, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0 with a carry of 1, 1 plus 1 plus 1 is 1 with a carry of plus 1 plus 0 is 0 with a carry of 1. Right? Now your E value becomes 1. Whenever your E is equal to 1, make the Qn, the last bit of your quotient, make Qn equal to 1. So my Qn becomes 1. After that, decrement the sequence counter. Clear? If it is not 0, repeat the same process. What is the first step? 1 second. Perform left shift operation. So perform the left shift operation, then you will get 10110 followed by 3 zeros 1 and a serial input of 0 will be transferred at LSB position. Next, after performing left shift, what you need to do? Subtract B. That means add 2's complement of B, which is 0 followed by 4 1. When you perform the addition operation, 0 plus 1 is 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. 1 plus 0 plus 1 is 0 with a carry of 1. 1 plus 1 plus 0 is 0 with a carry of 1. Whenever your E is equal to 1, set Qn equal to 1. Set Qn equal to 1. So your Qn will be updated and decrement the sequence counter. As it is not equal to 0, repeat the same process. So perform left shift operation, add 2's complement of B, and after performing the addition operation, check the value of E. As it is 0, whenever I perform this addition operation, I got my E value as 0. That means no carry is generated. No carry is generated. Whenever your E is equal to 0, what you have to do? You need to restore the value. That means you have subtracted B here. So you need to add the B here. What is B? 10001. 10001 is to be added. 10001 is to be added. Next, after performing the addition operation, decrement the sequence counter. You will not set any value F for Qn. You will set the value of Qn only if E equal to 1. Only in these two cases only you have set the value of Qn. If it is A less than B, that is if E equal to 0, you directly decrement the sequence counter. Don't set the value of Qn. Next, what happens? As the sequence counter is 0, as the value of sequence counter is 0, not equal to 0, repeat the same process, perform a left shift operation, and if E equal to 1, set Qn equal to 1 and decrement the sequence counter. This process will be repeated until the sequence counter becomes 0. Once the sequence counter is 0, you can stop the procedure. Where the result present for the division, you will have remainder and quotient, and your remainder is present in your A register and the quotient is present in the register Q. In Q register, you will have quotient, and in A register, you will have remainder. Clear? So with this, your division algorithm is completed. Did everyone understand this, ma? Or if you have any doubts, let me know the doubts. If you don't know, if you do not understand anything, please let me know in the chat box. If everyone understand this concept, we'll start the quiz. Is it clear for everyone? Please respond, ma. Is it clear? Okay, shall I start the quiz?